Hello, yeah, good evening, everyone. Welcome back to this session. So this is the third session we are conducting for this course. So now course is likely to going end, and now the week 11 I think is already released. So as I have already said in the previous week, so that week 10, 11, 12 are only based on the dynamic programming. There is no video content in the week 11 and week 12, but assignments are there, so that assignment will be count for your marks. Okay, so okay, Samir, do you have any specific doubt you can ask? You can turn on your mic, or you can also write in the chat. If you don't have any query, then we can discuss a little bit about the dynamic programming. Okay, so what is the dynamic programming, how we can use this? So any query, Samir, if you have? Okay. So let's discuss a little bit about the dynamic programming, because it this dynamic programming is a very important topic in the competitive programming. So we will discuss. So now Anurag is joined. Anurag, do you have any specific query for the session? Okay. Okay, so let's discuss a little bit about the dynamic programming, because three weeks assignments are based on this topic, dynamic programming. And this is also very powerful algorithm design techniques to solve many problems efficiently. So let me share my screen. Right. Okay, so I hope my screen is visible. My pen is now working. Okay. So thing is, what is dynamic programming actually? Okay, and why it is useful and how it is efficient. So we will discuss from the basics. So this is a one of the designing algorithm techniques. So we have another designing algorithm techniques like greedy algorithms we have seen in the initial weeks, and we have also seen I'm not sure that divide and conquer, so but some basic algorithms like merge sort, quick sort, you know about that. That is one divided algorithm techniques we have. Similarly, we have this algorithm design techniques, dynamic programming. So according to the definition of dynamic programming, so this is it is an algorithm techniques for solving optimization problem by breaking them down into smaller or overlapping subproblems. Okay, so we will discuss about this. What is the terms of this overlapping? All these terms I am just saying. So, and solving each subproblems only once, and storing the solution to avoid redundant computations. Okay, so what does it means by this solving each subproblems once and storing the solution to avoid redundant computation? So I'll take one example to explain this. So how we can reduce the computation, which are actually repeatedly the same computation we are computing repeatedly. So how we can reduce that type of computation by these techniques. Okay, so first thing is overlapping subproblems. So that will cover in this example. So let me just show you one example of this Fibonacci series. Okay, so this is one basic example that covers most of the concept of dynamic programming. So how we and most type of approach it will cover in the DP. So first thing, suppose you are calculating the nth number of Fibonacci series. Okay, so this is very basic problems. You all know that what is the Fibonacci series, the sequence we have. So let's suppose this is the type of Fibonacci series 0, that is start from 0, then 1, then each next term will be calculated by the sum of previous two terms. Okay, so 0, 1, next term will also be 1, and after that 2, then 3, then 5, then 8. Like this is the Fibonacci sequence, and we are looking for the nth number of Fibonacci series. This. Okay, so the naive solution we have for this, like you can see we have the recursive solution. I hope you are aware of this solution. So, and maybe you are also aware of the other solution for that. But we will discuss in the terms of dynamic programming. So, which solution is represent what? So here Fibonacci, we have the recursive solution and how this recursive solution works actually. So you can see what we are doing in the recursive solution. I hope you all know the recursive things. So recursive, and the function call itself, that's function is called recursive. So here in this function, we are taking n as an input, means we are calculating the nth term, and this is the base case. Okay, so this is the base case that will terminate the recursive process, and this is the recursive case. Okay, where we are calling the same function again, and we are passing the input like n minus 1 and n minus 2 in the both recursive function and adding this. Okay, so we will repeat this process. We will call this process for n input. Suppose we are taking 5 in this diagram. So this is the call recursive structure, how the recursive call are happening. Okay, so this is a top-down approach. We can understand that we are calling from the main function as fib5. After that, this function calls these two calls n minus 1 and n minus 2. So that is one side n minus 1 and this side n minus 2. Okay, and now this is a recursive process. So this tree structure actually you can see is now going in the same way. So that fib4 is a new problem, new sub problem, that is again calling to fib3 and fib2. Okay, like this. So this is the complete recursive call structure, and when we are reaching to the base case, so this is the base case actually, fib1 and 0. You can see the condition, if our n value is less than equal to 1, means 1 or 0, then it will return the n. Okay, same value it will return. But now in this complete structure, you can see how the same type of computations are repeating. Okay, so fib1 we have written direct value from here, fib0. So same things you can see, fib3 is calling this lower structure. Now fib2 is other side, it is calling the this part. Okay, same is on the right side of this fib5. So that is the same this other part, which is again it is computing separately. So in this structure you can see there are many calls which are repeating. Okay, so you can see this fib2, it is repeating here also, it is repeating here also. Okay, same fib4, fib4 is not there. Okay, so fib3 you can see here also and this side also. Fib1 is computed many places, you can see in this diagram. So this type of recomputation happening, and this is also called as a overlapping subproblem. Okay, so here subproblems are overlapping, so that are repeating. Okay, subproblem. So this all lower calls are, we can consider as a subproblem, and these calls are repeating. That means these are overlapping. So this is the naive recursive solution approach for to calculate this problem, nth number in Fibonacci series. And if you calculate the complexity for this, so this will become a 2 to the power n complexity. Okay, so that this is the recursive function. So you can simply calculate the complexity for like this, tn equal to 2, tn minus 1, okay, and plus 1, like this. This is the recurrence relation for this. If you will calculate the complexity for this, you will get a 2 to the power n complexity. And this is very big. Okay, this calculation is very big. So if you are getting n is large, so that will become much large. So how we can improve this? So the main idea of dynamic programming is to just reduce this recomputation, which are repeating again and again in this call structure. Okay, so here what we can do for the dynamic programming, if we store the solution of the subproblem when it compute first time, then if it comes again to compute, then we will not compute again completely, then we will check if the solution is already available, which we have stored previously. We will directly use the solution for it from our storage. So all this recomputation which are repeating, so you know that call structure is just like a first this part will be solved, and when we will reach at the last point, then it will revert back. Okay, so this part will be compute first time, then this part will compute. Okay, after that this part will be compute. So at the first time when we are computing any sub problem, we will store the result of that at any point. So you can see we have solved this. So fib2, what is the solution of fib2 is like 1 plus 0 is a 1. Okay. Again, if it is coming here, this subproblem is coming again here. So we will not call further. Okay. We will directly use our solution. So what was the solution previously for fib2? That we will directly return back here. Okay. So that is 1. 0 plus 1. Okay. So we will directly return back without calling further. Okay, so same like fib3 we have calculated here. So that if it is coming at this point, so we will not call further, and we will directly return the solution to from this position. So in this way, we are solving this overlapping sub problem, and we are using the solution of the sub problem without recomputing again. So if you see the next approach, so that is called as a memoization. Okay, so this is also a DP approach. So memoization is just like a word where we are storing our result. Okay, so here you can see what are the structure now after when we store the result of our subproblem. So this is the now solution code for this. We are taking the base case and we are storing this base case solution first time directly memo. So memo, we are just managing some storage data structure where we will store our data directly. Okay, and first we will check if our coming n value is in memo or not. That means this our sub problem already solved or not. So we will check our memory first. Okay, if it is exist, if this condition is true, then we will directly fetch our result. Okay, memo of n. Okay, so we are checking if it is not. Okay, in memo, then we will store the result in our memo by calculating the solution. Okay, otherwise we will return directly, return memo n. Okay, so here the calling structure is look like this. So our all the recomputed or overlapping sub problems are now removed. So in this way, you will see for the big problem also only the one child you will get on the right side for each, and this problem will be solved. And now this will become prox big of n complexity. Okay, so this is just like a one path. This will come as a like a constant term, so that it will remove. So complexity will be order of n, which is much better than 2 to the power n. Okay, so this is this technique is called as a memoization, and this is the DP1 approach where we are using the recursive steps. But here we are using some memory data structure to memoize the previous solution for sub problem, and we are reusing. Okay, if it is coming again. So this is the memoization techniques, and we also called as a top-down approach. DP top-down approach. Okay, so now next, how we can improve more, because still this is a recursive, then it will take some additional time for like stack things, maintaining the stacks internally. So you can see this type of memory we are maintaining here. So we are storing the result every time in this memory, and this will be filled only for n element because we are looking for the nth location. So this memory will be filled, and we will reuse solution. Okay, now that comes to the next. So that is this is also a basic dynamic programming, but this is called as a bottom up. The previous one was also dynamic programming, but that was the top down approach. But now this is a bottom up approach or a tabular approach. Okay, in the dynamic programming. So here actually we start with the smaller problem first. Okay, means we solve the sub problem first, and we use the solution of sub problem to achieve the solution of main problem, like this. Okay, So previous problem we start from the top, we called recursively till the end, and then we store the solution and we use it. But here we will start from the sub problem. So means we are starting in this diagram, you can see. So we know that the base solution is like fib 0. We have the solution for this is 0, because we first that first term for the Fibonacci series is always 0, and this is the 1. So this is the sub problem. Okay, we are looking for the nth term. So what we will do is we will start from the bottom of it. So sub problem. So we have the solution for this sub problem. We have the solution for this problem. Now we will reuse the solution of the previous sub problems and we'll get the next solution. So like to get the fib 2, we will just take the value from the fib 0 and we will take the value from fib 1 like this. Now we will get a 50 and this one. Okay, so we will repeat this process, and like we have like 0 1. So for to get the next term, so 0 and 1. So this is 0 plus 1 1. Okay, now to get the next solution like this, 1 plus 1 2. So this type of approach we are getting. So we are starting from sub problem now. Okay, and this is the bottom. Bottom means starting from the smaller problem or sub problem, and using the optimal solution of the sub problem and achieving the final means solution of the main problem. Okay, so this is called as a bottom-up approach of the dynamic programming, and this we can achieve without recursive and simple table form, either one-dimensional array or two-dimensional array, depends on the problem, and the complexity still will remain order of n for this, but it is more efficient compared to the recursive one. So these are the three examples I have seen. So this is called as a dynamic programming approach. Now another thing is, so some basic theoretical things. As I said that there are some key properties of the DP problems. Okay, so what are the key properties? I've already said one, overlapping subproblems. So any problem. So how we can identify that any problem can be solved using DP or not. So problems should have key properties. So these properties are like first is optimal substructure property. So any problem that contains this optimal substructure property. So what is this property actually? If the optimal solution to a problem can be constructed from the optimal solution to its sub-problems, then this problem can be solved using a DP approach. So means what we are doing actually, we are calculating the optimal solution of the sub-problem, and we are achieving the optimal solution for the main problem by using the optimal solution of sub-problem. So this property that a problem should have, so problem can be solved using this structure. So that is the one key property for the DP problems. And second is this overlapping sub-problem, which I have already discussed. So if the same type of computation happening again and again, so we will reuse the solution of the sub-problems to get the solution of main problem. So that is another property is overlapping sub-problems. Now the thing is, what is the difference between dynamic programming versus divide and conquer? Okay, so that is also a one question, because divide and conquer also divide the problem. Here also dynamic programming, it also divides the problems. Okay, we have seen that we are breaking the problem into a sub-problems using the recursive things. But divide and conquer, so this is a very common question. So divide and conquer actually break down a problem into independent sub-problem. Okay, so where the problems, sub-problems are independent to others, and each independent problem solved separately, and after that we combine the solution of sub-problems to get the final solution. Okay, so that is the idea of divide and conquer, merge, and where we okay, so there are example like merge sort, quick sort you have seen. So where the sub-problems are actually independent. So this is the key point of this divide and conquer. And dynamic programming actually break down the problem into overlapping sub-problems. Okay, solve each sub-problem only once and store the solution, and where the sub-problems are dependent. Okay, so other sub-problem solution is also dependent maybe on the other problems. So this is the key difference in the dynamic programming versus divide and conquer. And dynamic programming versus greedy algorithms. You have already seen the greedy algorithms. So greedy algorithms that it makes locally optimal choice at each steps with the hope of finding a globally optimal solution. Okay, so but there is no guarantee that you will get a optimal solution, right? For this, you need a proof. So I hope you have seen some example in the initial week 2 or week 3 when we have discussed the greedy algorithms. So like coins problem. Suppose if you have set of some coins. Uh, so like you have the coins like 1, 2, 5, 8, 10. This is the value of coins. Okay, so this is the value of coins, and you have the infinite number of coins for each value. Now some amount is given, like you have given like 30, and we are asking that what are the minimum number of coins required to achieve this 30 amount. Okay, so this problem looks very a greedy type of approach where we can apply here directly. Okay, so this looks like, so always just sort the coins value and always pick the highest value coins. Okay, so let's check that you have the value of 10 coins. So just take 3 coins of this 10 value and you will get it. It's 30 amount and 3 coins are required. And this is the optimal solution, and it looks correct also. Okay. So most of the time you will feel that this is working on some test cases and it is correct. But this is not always true. So suppose the example is given like this. So 1, okay, and 2, and 6, and 7, and like 10. Okay, so here suppose average amount is 30. Okay, so if you apply the same approach, okay, same greedy type of approach, means always picks the greater value coins first and check how much you are getting. Okay, how much coins you are getting. So 10 you will pick, only you can take 1 coins into 10. So you are getting 10 amount. Now 3 is remaining. So you cannot take 7, you cannot take 6, you can take 2. Okay, only 1 coin of 2. So 1 into 2, you are getting 2. Now still 1 remaining. So you will take 1. So 1. Now total amount is covered. So total 3 coins you can see we required by this approach. But this can be done in by 2 coins. 6 plus 2. Sorry, 7. Okay, so 13. Here you can see this is now greedy approach is failing. So greedy approach works, but not always. Like some shortest path algorithms are there where greedy algorithms works actually. Okay, so but that require proof that your algorithm is always will work fine. Okay, so that is greedy, but in that case we required dynamic programming, where actually that dynamic programming checks the each possibility in the smarter ways. Okay, without recomputing the things. So this is the idea of like dynamic programming versus greedy algorithms. So what is the greedy algorithms? We always locally optimal. Actually, we choose the locally optimal solution at each steps. Okay, to find the globally optimal solution. So this is greedy approach, and I have discussed that top down with memoization approach I have discussed, and bottom up with tabulation approach that I have also discussed. So I have some another problem also to show you this. So like this is the solution in all the things. I hope this link you have. I have shared this link in the previous meeting. So let me share in the chat again. If you can, if you want to visit this, some problems example is given. So you can check those example. Okay. So in the dynamic programming tab, there are problems, and there are some additional problems you can practice, like competitive problems for practice. So you can find out some DP problems to start. So now this is the one example, and this is the another problem you can see, dynamic programming problem, grid path problems. Okay, so this is the one grid path problem, and scenario may be different. So, okay, I'm just directly pointing out what is the problem, but this problem maybe comes with some different scenario story, so that become a competitive problem. Now you can see this is one grid type of we have structure we have, and we are using the border lines all or lines as a road. Okay, path, and this is the starting point, This is the starting point. Okay, so 0 0, and each has like 0 1 2 3 4. This point is this side also 0 1 2 3 4 5. Okay, like in this way. And we have this top. So this top point, this is the corner point 5 10. Okay, so we want to find out that how many unique paths are possible in this problem from 0 0 to this 5 0. Okay, so some examples are given you. So there is a thing here. You can only move to up or right. Okay, you cannot move to back side of this problem. Okay, so here you can see you can only from this any point you can only move to right or up. So what are the maximum paths are possible for this? Okay, so this is the problem, and now this looks very tough problem. So this is very straightforward. There is no condition are given, but later you can see the another version of this problem also. So that is just like if you have some blockage. Okay, suppose if you have some blockage, so you cannot cross this point. Okay, you cannot cross this point. Then how much unique paths are possible? Okay, so this is a different version of this, but initially this is the one. And regarding the solution, how we can solve this using the inductive structure. So we can start. Uh, let me show you. So yeah, we can use this inductive structure approach for this. For each next point, we can solve this either horizontally or vertically in any way. So this is the inductive structure for this. For each point, we will use this. Some initial setup we have. Uh, we have the initial setup. So okay, I'll explain in the that grid only. But this is the main inductive structure for this. So to calculating the all path for any point. So just take the what are the value of the left path, okay, and what are the value of the right path, and just add up this value. So you will get a total number of path possible till this point. Okay, initial setup you have to do like this. So let me just show you. So like this. Okay, so what we will do, because you can only move to this direction only in the one path using the one path only. So from this point you can only move to this direction. Okay, so because of that we will initialize the one value at each. Okay, this lower value. Okay, because you can only use one path for this direction. Same for this direction, you can only use one path. So we have set it one possible path value for this point, each point. After that, we will use that. So this is the initialization for this problem. After that, we will just use the process, that inductive structure for this problem, and we will store our result. Okay. So that is just like it to calculate the total number of path at this point. Okay. So this is like a 0, 1, and this is because of 1, 1. So how many paths are possible at 1, 1? So just take the value. What are the possible path at this point? So means 1, 0 and 0, 1 like this. Okay. So this. So just read the value from this and read the value from this and add. So that is the value for total path for this point. So 2. Okay. So means you can come from this path only, or you can come from this path at this point. So 2 paths are possible. So you can solve this either vertically or like this way. So now getting this value, you can calculate this value. So just take 2 from this side and 1 from this side, and now this is 3. Okay. Now same things, 3 plus 1, 4. So you can complete this point. Now you can move to the next. Okay. So for getting the total number of path at this point, so 1 plus 2 is 3, and 3 plus 3 is 6, like this. Okay. In this way, so what is the size of like the total size of this grid? That is 5 and 10. So total number of steps are required 5 into n. So if we just consider as a n in row and m column, so n into m is the complexity for this. So this is just like a same recursive structure where we can use memoization techniques we can use, and recursively we are solving this. And so and finally at the top we will get our total number of path value. So at the point you can see total 1358 unique paths are possible in this. Not this is not correct actually. Okay, so here actually this solution is given because here it is considering that block is. Okay. So now what is the solution for blockage actually? So at any point, if blockage is given, just take the value 0 at that point. Zero path is possible on that point. Okay. So now the other thing is will remain same. So here the 2 points are given this as a blockage. So just mark as a 0 value at that point and then repeat the same process. So 6 plus 0 is 6 at this. Okay. And 26 plus 0 is 26. And do the same process again. Okay. Now you can solve this cross point where the blockage is also there. That problem you can also solve using this. But this is the okay. So this is one memoization way how we are solving this. Uh, Now the another way to solve is so let me just discuss the comparison between memoization and dynamic programming. Okay, with the respect of this problem. So what happens? Suppose if blockages are given like this. Okay, so blockages are given like this. A second. Okay, so you can see this is the border actually, all blockages, and you are starting from that 0 0 point. Now, what will happen if you solve this using the memoization techniques? So that memoization technique it solves. So all this is are actually 0. Okay. So here actually the advantage. Otherwise, that bottom-up approach is better. We have said that already previously, but sometimes top-down approach is also good. So this is the example for the top-down approach. So if we start from the bottom up approach using the memoization techniques, so what will happen? We will solve all the parts. Okay, so we will solve all the part and completely. And at this point, after coming at this point, we will get this all fields are 0. And now the previous calculation is just like a wasted. Okay, now you will get the 0 value from here and this one value from here. Okay, like this one. So there is no used for this yellow highlighted part. Okay, so bottom up approach will solve each thing. But if you start this problem with the top down approach, okay, so that is you will start from this point and you will call this side and this side, okay, recursively. And from here you will call this side and you will get this side. So here you will get a 0 and blockage. So you will not call further. So this is like a base case for this recursive call and your call will stop at this point. So in this case, your recursive call will only move to this side till this point and this point. And this highlighted part will not be calculated by this top-down approach. So in this case, this top-down approach is better than bottom-up approach, like this type of scenario. Okay, so here this is more efficient. So both are the dynamic programming approach. You can think that which one you can apply and okay, so both you can think. So in this page, we have given the solution of each type of recursive. You can see the simple base recursive solution is given. And after that, memoization technique solution is given. And then finally, tabulation method that, okay. So all type of solution is given. So some more problems are given. So these are the basic idea of how we start with the naive approach recursive solution, and then we can you converted that recursive naive solution to that top-down approach using the memoization. Okay, or we can think about the bottom-up approach. So that bottom-up approach thinking is a little bit tricky. That comes up. You will be familiar after some practice, after solving some easy problems first. Okay, because how you can figure out that how where from we can start with the sub problems and then how we can get the optimal solution for the final solution. Okay, so bottom up approach is little bit tricky to figure out. Otherwise recursive solution is just like a find out the each possibility and then use the memoization to reduce the computation. So this is the basic idea. So you always can think about the recursive solution first, and then you can say, think about the top down. Okay. So this is the main idea of dynamic programming. So now all the week 10, week 11, and week 12, these three weeks are based on this dynamic programming. Okay. So in this space, you can see this. So this was the solution for grid. Now you can see longest common subword. So this is also very standard common problem. So if you are given two words, okay, and you want to figure out that common word. Word means continuous sequence in two strings. What is the longest common continuous sequence in two strings? So how you can do this? So we can use this inductive structure to fill this matrix and get the solution. And after that, you can see longest common subsequence where the character can be skipped. Okay. So like what is the longest common subsequence? So some problems are given like based on 2D array based, 1D array based, so that you can go on this, or you can solve some basic problems. You can start with basic problems to get the idea of this dynamic programming. So this is the basic idea of dynamic programming, and you can start with this with the basic problems. Okay, so if you have any query, you can ask. So some more are joined now. So any query from anyone, you can also write in the chat. I hope you have the idea of the calculation of assignments, score, like how will it will calculate. I have already discussed in the initial weeks. So there are total 8 weeks, sorry, 12 weeks assignments we have. Okay, 12 is week is not released yet. It will released. You have total 12 week assignments. So each week have quiz assignment and some programming assignment also. So how you will get the score for 25 marks? So that is just like a best 8 your quiz score. So like I'm just writing this formula. I hope this is clear for you. So like 25% marks will be taken from your assignment. So how that will calculate? So 12.5 marks. Okay. So that will be calculated like best 8 out of uh, total 12 quiz assignment. Okay. And the same 12.5 marks will be taken from okay, so here we will count the problems. Total how many problems we have in the all 12 weeks programming problems. Okay. Suppose we have like 24 problem. I'm just taking the example. Okay. So you can just simply count the problems. So what is the same ratio we have? Like we are taking 8 out of 12, means 66.66% approx. So this is two-third. Okay. So same two-third we will take from this total number of programming assignments. Okay. So best two of third problems. Okay. Programming. Okay. So 12.5 marks will be taken from your best 8 out of 12 quiz, and 12.5 marks will be taken from best 2 by 3 problems out of total problems, programming problems. And that will be coming total 25 marks for this. Okay. So yeah, this is the scoring formula for this. Okay, now so yeah, that's it for dynamic programming. So this is the last topic of your course. So this 10, 11, 12, all the contents are related to this. If you have any specific query, then you can ask. You can also write in the chat if you have any specific query in the course. And exam pattern will remain the same of your quiz pattern. Okay, so there is no programming exam for this. Only the quiz quest type of questions like MCQ, multiple select, or numerical input type of questions will be there in the exam. And the same type of pattern, same type patterns questions will be there. Okay. Okay, so if there is no query, then we can close the session. So this was the total basic idea of DP we have discussed, and just solve this. And after this course, also just to practice on the competitive problems to improve your efficiency. Okay, any query, anyone, or shall we closed? Okay. Okay, thanks everyone. If no query, then we can close the session. Thank you.